So the problem example that you see on your screen consists of two hollow cylindrical pipes which are connected by a cap plate. So this is a problem from one of your textbooks, the Geary and Goodnow textbooks, example 1.5. So you might as well, when you get time, just take a look there also if you want. So let me just maybe start marking or try to understand the problem first before or understand the system first before I pose the questions, and then let's see that how we go ahead and solve it, right? So what you have here are two hollow cylindrical pipes. This is the pipe 1, this is the lower pipe which is over here. So maybe just for starters I will go ahead and mark these guys. So this is my upper pipe and this is my lower pipe, right? So let's see what is given in terms of the dimensions and so on. So it says that the upper pipe has a length of 350 mm, it has an inner diameter of 51 and an outer diameter of 60 mm, right? And then the lower pipe, also a hollow pipe, it has a length of 400 mm, slightly longer than the upper pipe, and an inner diameter of 57 and an outer diameter of 63. Now just to demonstrate, this is probably a way to just imagine how it looks like. So maybe this is one pipe, this is one hollow pipe that you see, right, where you have, this is the outer diameter and this one is the inner diameter inside. So this is maybe the bottom pipe and you have a top pipe, right? So these are sort of connected together. Maybe if you put glue around the rims of that one, so it is sort of glued together over here, so you have a kind of a system, right? Now so you have two hollow pipes essentially. This is the upper one and this is the lower one as marked in this particular figure over here. Okay, now let's talk about the loads. It says, as you can tell, that the load PA, there is a load PA over here which is 7,800 newtons or 7.8 kilonewtons at the top, right? Now see how this load PA is being applied. So after you have sort of glued it, and remember the top is fixed, over here, with some plate or something, right? So you are applying this load at this particular point in here at the juncture. You're applying this particular load, right? Now remember this load here is shown in terms of these smaller arrows, right? So these arrows do not represent the stresses, it is the total load. So maybe if I wrap my finger around it and try to apply the load, this is the total load which I'm applying is 7,800 Newton. And at the bottom you have another load PB which is acting over here. So maybe a way to imagine that, suppose if you connect a thread here and if you're pulling the thread, right? So that is the load PB over here. So I hope the system is clear to you. I will explain it once again. One hollow cylindrical pipe, another hollow cylindrical pipe which is sort of welded together maybe, right? And the upper pipe is fixed somewhere, and the loads which are acting on the upper pipe is 7.8 kilonewtons, and on the lower pipe is a particular load P, right? So now let's go ahead and let's see that what are some of the problems the question asks, right? So the first problem, it says that find the load PB so that the tensile stress sigma in the upper pipe is 14.5 MPa. Right. So, and for this case, it asks, the part B of this question is, what is the stress sigma in the lower pipe, right? So let's revisit the problem again and try to understand, right? Now think that if in this particular system, I'm presenting the system again, if the top part of this is fixed over here, now imagine that there is no PB over here. Suppose, let's just forget PB, there is a PA which is acting over here at this particular juncture, right? Now if my top is fixed, right, imagine this is fixed, and if I am pulling at this particular point, at this particular juncture where my fingers are over here, these fingers, if I'm pulling over here, right, since the bottom is free, which pipe will get stressed? The top pipe will get stressed, because the bottom just simply will go as a rigid body motion, it will go, right? Now on the contrary, when you are pulling this bottom with this force PB over here, then both the lower pipe as well as the upper pipe will undergo some amount of stress, right? Again, to reiterate, if you're just pulling with this force PA over here, only this pipe gets stressed, this pipe undergoes no stress because this pipe simply moves down, because this pipe undergoes some amount of stretching. Whereas when you are applying this force PB, since this is a continuous system, this pipe gets stressed as well as the upper pipe gets stressed as well. Okay? So the first question asks that find PB so that the tensile stress sigma in the upper part is 14.5 MPa. right? Now we remember that from the discussions we had before, that we know that our sigma is nothing but P divided by A. This is the general formula of calculating the stress, right? Now we are calculating the stress, remember, for the upper pipe. So for the upper pipe, first we have to calculate what is the area of cross section, and also we need to find that, you know, what is the load, what is the P which is acting on the upper pipe over here, right? So to calculate that one, so for the upper pipe, for upper pipe, right, if I calculate the A, it is going to be pi the outer diameter d2 square minus d1 square divided by 4, right? So this I have already calculated. So this value comes out to be, let me check, this value comes out to be 784.61 mm square. Okay, so this is the area of, you know, this upper pipe that you have over here, right? Now what is the load acting on the upper pipe? As I said, since this is a continuous system, the load acting is PB plus PA over here, right? So the question asks, that question gives you the sigma and asks you to calculate PB. So what we have over here, that if I again rewrite this particular equation, that sigma for the upper pipe is PA plus PB divided by area. Maybe I mark this area as the area of the upper pipe, right? Let me just go ahead and mark it again. This is the upper pipe and this is the lower pipe, that is A. So the sigma of the upper pipe is PA plus PB divided by A, which if you you have to find this particular parameter PB over here, this particular guy. So this essentially, you're given the sigma, so this is 14.5 megapascal. Megapascal, remember, is Newton per mm square, is equal to PA is given as 7,800 Newton. That is, so I'm keeping in the Newton units only because my megapascal over here is Newton per mm square. So 7800 plus PB divided by 784.61. This I'm also keeping in mm square because this is in MPa, right? Now if you solve this one, what you would get is your PB comes out as 3577 newtons, right? So this is part 1. This solves my part 1 of the problem. Now part 2 of the problem asks that for this case, like when PB is 3577 Newton, what is the stress in the lower pipe? Now remember, the lower pipe, the stress in the lower pipe is only going to be because of this load PB over here, because when you are pushing from the top, if just PA was there, this one will just go a rigid body translation. So the stress which is acting, or the force which is causing the stress in the lower pipe, is simply because of this particular force PB, right? So we have to calculate the sigma in the lower pipe. So let's just write that. So sigma in my lower pipe is simply going to be PB divided by the, so this will be area of the upper pipe, sorry, this will be the area of the lower pipe, right? So area of the lower pipe is what? The area of the lower pipe we calculated, or we can calculate the area of the lower pipe is pi d4 square minus d3 square divided by 4, right? So that area comes out to be 565.5 mm square. Now if you substitute this one, if you substitute this area over here and this PB back over here, then we are going to get the value of the, you are going to get the value of your PB, which comes out as of your sigma of the lower pipe, which comes out as 6.33 MPa. right? So I hope it is clear to you how we did this particular problem. So for the first one, what we did was that we were supposed to calculate the load PB for which we are getting this particular stress. So we know the upper pipe is getting this, the load, total load which is coming on the upper pipe is PA plus PB divided by the area of the upper pipe. So with that we calculated the load. The second part asks to use the same load and to calculate the stresses which comes in the lower pipe, which is quite straightforward. You have the sigma in the lower pipe as the load divided by the area of the cross section over here, right? So this question has one more part, so let's go on to this, move on to the second part over here. So in the second part it asks that if PA is unchanged, right? So the PA is still 7,800 Newton. So PA is 7800 Newton. Find the new PB such that the sigma is same for the upper and the lower pipe, right? So it says both in the upper pipe and the lower pipe. Let me mark this again. So this is my upper pipe and this is my lower pipe. The sigma in the upper pipe is equal to the sigma in the lower pipe. So that essentially means that what we are trying to find is your sigma. Let me change my pen color. That is the sigma in the upper pipe must be equal to the sigma in the lower pipe. This is what it asks, right? So sigma in the upper pipe is equal to sigma in the lower pipe. So this essentially means, again, if we just boil it down to the basic set of formulas that we have, again we know that in our upper pipe is subjected to both PA plus PB, whereas the lower pipe is subjected to just PB over here. So what we have that PA plus PB for the upper pipe is going to be simply PB divided by the area of the lower pipe. Now in the previous page we have already calculated these particular values of your AU, the area of the lower pipe, right? PA remains unchanged, so the PA in this particular one is 7800 Newton, because it says the PA remains unchanged over here. So the only question is now for you to calculate what is the PB that you get. Now if you substitute the numbers and everything, what you are going to get, that your PB comes out to be 20, PB comes out to be 220.13 kilonewton, right? Or 20130 kilonewton Newton, right? So this is what your PB comes out to be. So that solves your this particular question. Now the second question, it asks that for this load, for these loads, find the tensile strain epsilon. Remember, the stress is represented by the Greek symbol sigma, and the normal strain is represented by the Greek symbol epsilon, right? So for the strain, find the strains in the upper and the lower pipe if the upper pipe elongates by 3.56 mm and the downward displacement of the lower pipe is 7.63 mm. So let's again try to understand the system that we have over here, right? The elongation of the upper pipe happens over here. So the upper pipe elongates over here, and it says that for the lower pipe the downward displacement is 7.63. So this one has an overall displacement of 7.63. So what is the stretching of just the lower pipe? It is going to be the stretching, the total displacement minus the stretching of the upper pipe that you have over here, right? So let's maybe tackle the first part. The first part says is that the upper pipe elongates by 3.56 mm. So we can write that epsilon of the upper pipe is going to be, remember the strain is what? Change in length divided by the original length. So epsilon of the upper pipe is 3.56 mm divided by the original length, which is 350, right? So both are in mm units, so that works out fine. So this one comes out as 1.017 into 10 raised to minus 2. Remember, it is strain, so it is unitless, length divided by length. And epsilon of the lower pipe, as we discussed, that the lower pipe, the deformation of the lower pipe is going to be the total displacement minus the deformation of the upper pipe that you have over here. So this is going to be 7 0.63 minus 3.56 divided by the length of the lower pipe, that is 400, right? So this one comes out to be the same strain, 1 point. If you calculate that one, you will see both the numbers sort of line up, it matches up over here, right? So I hope this is clear. I hope the second part of the problem was clear. Remember, this one that you calculated, this is the actually the delta of the lower pipe that is there. So this completes our particular problem. So we have solved part A and part question number 1, question number 2. Both questions had 2 parts, the part A and the part B.